Welcome, class. Good to see you again, even though I don't really see you. Today we're going to be talking about an idea called resolution. This is something that we do encounter every day, but we don't really think about it too much. This is a topic that's highly connected with diffraction, with single slit diffraction, with diffraction gratings and stuff like that. Now this topic is 9.4, by the way. If you have your data booklet, you probably want to go to 9.4 in the data booklet. This topic has two very distinct sections. So this video is going to be focused on resolution through a single slit. Resolution of two objects through a single slit, and some of the first equation you see in that chapter. The next video I'm going to do is going to talk about resolution as it applies to diffraction gratings. Very, very different topics, and so I did want to split that up a little bit. If you'll notice on the screen, we have a situation. Let me explain it here. You see this little object down here. We'll call this object A. Object A is producing light. Maybe it's a star out there in the sky. And the light from the star is going all the way through space until it enters an opening. It enters maybe your eyeball, your pupil, which is a small opening, and the light is diffracted. All the light that goes into your eye is diffracted, and it makes this nice little pattern. You see this diffraction pattern, and we've done stuff like this before. So we can calculate the angle to the first minimum. That's going to be an important angle for us. Now, if this is a rectangular slit, so for rectangular, actually, I'm going to put this over here. For rectangular slit, that angle to the first minimum is the same equation we've been using for quite a while. Theta equals lambda over b. However, if you look in topic 9.4, you see something slightly different. Because honestly, often in the resolution chapter, they're not going to talk about seeing things through really small openings. Instead, they're going to talk about seeing things through round openings. It's like your pupil or a telescope. So if you have a round opening, that is often called in IB language an aperture. It's for Portal fans there, aperture science. We're going to use the equation theta equals 1.22 lambda over b, where b in this situation is diameter of opening, or aperture, I guess. Lambda, theta is the same theta as before. This is the angle to the first minimum. It's going to be an important equation for us to use. If you ever talk about an aperture, make sure you use that 1.22 equation. Really, resolution is the only time you're going to see that, so you don't have to worry about it too much and other stuff. But that's where that first minimum is. So inside your eye, there's a diffraction pattern. You see this dot. You see object A. Let's say object A is a star. And so everything's good. But let's imagine we're seeing two objects. Let's imagine we have another object right here, object B. Okay, I'm going to erase all this real quick just so we can free some things up. Let's imagine, we're seeing object B. Whoops. Okay, same slit opening, all this kind of stuff. Object A is going to make that single slit pattern you see right there, but object B, which is going to come into the slit at a slightly different angle, it is going to make a different type of pattern. Let me get another image here. Okay, it's going to make another diffraction pattern somewhere out here. So inside your eye, right where your retina is perhaps, you're going to have two diffraction patterns. Now let's imagine that what you see on the screen right now, those are the two diffraction patterns. Would you be able to distinguish both A and B if those were the two patterns that are hitting your eye? I want you to think about that for a second. Do you think you'd be able to distinguish it? Now think about your eye. Your eye is just sensing all the information, so it's just going to add up all the information. And in this case, yes, you would be able to tell A and B apart. We have a word for that. The word about whether we know you're going to be able to tell two objects apart is called resolve. Will you be able to resolve the two images? Will you be able to tell them apart? But it could be where A and B are so close that maybe they look something like this. So those two images are right on top of each other. All your eye sees is the sum of those two images. Will you see one object or two? Hopefully you said you will see only one object. That's exactly right. I want you to imagine looking in the sky and seeing a galaxy. If you see a galaxy is full of billions of stars, but you only see one dot. There is no way your eye can resolve or tell apart all those different light sources. There are light sources that are separated by light years from each other, but their angle from where you're looking at them is way too close for you to ever tell them apart. But you get some objects like a telescope with a much wider aperture, some Arecibo, giant apertures. They can start to resolve these objects. Telescopes can actually see into distant galaxies, and they can tell the different objects apart. That's not because they're better than you, it's just physics. If you're in an airplane and you're coming down to land, when you're in an airplane looking at a city, you see dots on the highway. Maybe red dots for the taillights of cars and white dots for the cars coming at you if you're landing at night. As you get closer and closer to the ground, eventually what happens is that one dot per car turns into two dots per car. You see both red taillights or both white headlamps. This is what happens when you are all of a sudden able to resolve. Now, so we agree that right here in this situation on the board, this would not be resolved. We would hopefully agree that something like this would be resolved. So the question is, where in the middle, where are we going to say it's going to be resolved? And the answer is this. In order for an object to just be resolved, I'm going to write this down. This is what we call, by the way, Rayleigh's or Raleigh's criteria. Criterion, I don't know. In order for two objects to just be resolved, that means that the angle between them is as close as possible. Any closer, you will not tell them apart. Any farther away? Yeah, sure, you still see them apart. The minimum of one wave must match the central max of the other. So in other words, the central maximum and the first minimum, they've got to meet up. That is the definition for being able to just be resolved. Let me show you a picture here. I'll post it over here on the right. I'll post it down here. So we see a situation where on the left side, these two images are obviously resolved. You can obviously see them as two separate objects. Here you just see them apart. You just see your eyes, which are, you see a picture here of them summing together the two waves. You can just see them apart. Here the two waves are just right on top of each other, and you're just going to see one object. This is like seeing a dot in the sky and saying that that's a star when it's really a galaxy. So Rayleigh's criteria, in order for two objects to just be resolved, the minimum of one wave must match the central max of the other. Now you say, okay, that's great. Understand that definition, super, but how are we going to use this? Well, here's what we're going to do. Most problems, when we're talking about this equation, they're going to ask you questions like, can you resolve the two objects? How close do you need to be to resolve the two objects? So let me do this. I'm going to sort of copy some of this from above, just to simplify things a little bit. Okay, I'm going to place these two diffraction patterns where we are just resolving them. So something like that looks pretty good. Okay. And then below, we are going to add we'll do this. We're going to add a single slit. We'll call this an aperture. All right. And we have two objects. So here's pattern for A, pattern for B. So here's A over here. Of course, the light is traveling straight through to there. And then here's object B a little bit to the left. And so we want to be able to answer questions like such. We want to know, first of all, at what angle do these have to be apart from each other? So if I draw a line for object B, let's draw the line in pink here. So let's say here's the line to that, here's the line to this. Well, we have an angle. Okay, we have an angle, and we actually have an equation with this angle. This angle, if we're at the point where we're just resolving objects, this angle is the angle to the first minimum. Or for an aperture, theta equals 1.22 lambda over b. Now, knowing geometry, I know that same angle exists right here, where a and b are separated by that angle. And if we define two other terms, let's define x as the distance between them, and capital D is how far away those objects are from the aperture, then I could say that theta, using the small angle approximations, only works for small angles. Big angles don't need to apply for resolution. Theta is also going to equal x over d. And so we can put these two equations together, and we can form an equation like such. We can say 1.22 lambda over b equals x over d, where x is a separation of sources. So that's right here. These two sources are separated by x. And capital D is distance from aperture. Aperture could be a telescope, it could be an eyeball, like a pupil in an eyeball, whatever. From aperture to source. And so using this equation, knowing the wavelength of light, you'll be able to figure out, and knowing the size of the opening, you'll be able to figure out, can you resolve those two objects? Right? So I'm going to let you work a couple problems with that. I'm going to have you read through the book and try a few problems like that. Let me just work one right here with you, sort of an interesting problem. Let's imagine you have two green lights are set up where they are just resolved. So you're holding two green lasers maybe right next to each other, and you're far away from these two lasers. You're looking at them through your eyeball, and you can tell there are two lasers, but you can just tell. If you go any further away, it's going to look like one laser. This is something we would do in the hallway, but can't do that. So they are just resolved. Now here's the question. If we switch to red light, will they still be resolved? All right, so if I look at this equation, again, I'll write down the equation 1.22 lambda over b equals x over d. So x is the minimum distance that can be separated. Now, in this equation, what happens to my wavelength as I go from green to red? This is something IB will want you to know. If you go from green to red, what happens to the wavelength? Red is the biggest wavelength of visible light. Wavelength goes up. So wavelength goes up. Let's use the eraser there. Whoops. Wavelength goes up. The opening is going to stay the same width. You're still the same distance. But what's going to have to happen to the minimum distance between the object? The minimum distance between the object is going to have to go up. In other words, in order for you to resolve those two red lights, they're going to have to be separated. Or we can look at it like this. Or let's say we keep them the same distance apart. The distance I am from the red lights is going to have to go down. I'm going to have to get closer to be able to resolve those lights. So will they still be resolved? No, they will not be resolved. That's the kind of questions they do like asking with resolution. So I want you to read in the book. I'll give you a book assignment as far as what pages and all to do. I want you to try the worked examples, see how those work for you. And then I'll be back in the next video talking about diffraction gradients. Hope you're well. This is Mr. Reynolds.